get started. So last class, we started something very important, how we can design a processor. We said it has multiple steps, but first step is very important step, and is to specify what's supposed to do. Processor, what's supposed to do, what instructions we have. So that was the first one, defining ISA, instruction set architecture. And the second state was when you have instruction, you need to see which components you need. Like if you need adder, if you need, for example, memory, if you need whatever program counter, register file, whatever you need to consider those and then assemble them in a proper way. And however, this structure that we mentioned was for one cycle processor. So every instruction can be done, completed in one cycle from the start of the edge to the next edge. And then when we have components, we assemble them together, we connect them together, they connect with buses, and then we can talk about control part. Control part coming with the specifying control inputs for each of these components, and then assembler controller. We design most of the time combinational logic for controller, but you can use microcontroller too to just do that. Sometimes controller is hard and you need to change it many times. And then after that, you need to, because the structure that we use is an incremental method or iterative method, we just need to run it multiple times, find, if there is an issue, if there is a timing issue, we need to make it better, optimize it. And if we want to add new instructions, we can add. If we have that structure ready, you can add some other instructions. For example, if you made a structure for R-type, register type instruction, you maybe just work with add and subtract, and then you add other instructions as well in that category. So this was something that we started last class, but still we need to talk about that more. Today we're going to continue with a simple, simplified version of RISC-V. When I'm saying simplified, means we're going to bring down number of instructions. Instead of having many instructions that we had, we just want to have a processor simplified version of RISC-V to just have R-type, register type, when you are working with two registers and put that result in another one. Immediate type when you have a constant in your instruction and you want to add, for example, one register with an integer number like 5 and put the result in another register. And then this is immediate type. And also we have a S type. S is just for a store, because load is kind of same as I type, but a store type, a store is a little, a difference. And then for jump, we have another type is J type. When you want to jump, you need to have different style of structure. In this class, we're going to learn how we can make instructions. Instruction is one of the parts. I always ask in my exam, okay, we have a computer doing these operations, and please design one instruction for memory, access to memory. You need to do that. How we can do that? You need to say, okay, first of all, what is the size of instructions? For example, in my question, I tell it's 16 bits. You consider, okay, all is 16 bits. And then I'm saying we have 16 instructions in overall. So when it's 16 means opcode need 4 bits. And then more information, for example, I'm saying, okay, we have 8 registers in this specific computer. So based off that, you know how many bits you need to consider for register destination and how many you need for source. You know, based on that, you might have some extra registers that can be used for other purposes. So this is designing instruction. So we're going to see that also today. Okay, so let's get started. So we want to design a processor today. It's not hard. You can see after this class, you can see, oh my God, this is not that difficult. As far as you simplify that, make it modular and use some stuff that you learn in the other classes, and like Verilog, for example, going to help you to write most of this part very simple. And we can see how we can do that. The first step is to see this processor that we want to design, how many instructions and how many type instruction and what instructions has. So in this computer, we consider memory instruction, same as RISC-V, but we just have 2 memory instructions, and it's load a word. And word is 32 bits, of course. Load a word and store a word. Load and store are the kind of instructions that's similar to RISC-V. We had in RISC-V too, like that. We want these 2. This is one of the categories. The other one is arithmetic and logic. We want to have add, sub, and or immediate. So we have immediate instructions as well. And we have branch and control instructions. So we need to, if you want to design if you want to select the component, we need to select components that can be used in these instructions. For example, do we need memory for these instructions? Memory is one of those components. Okay, I'm asking you guys, do we need memory? Why?
We have store and load.
Yeah, we have store and load. So we need memory. Do we have ILU? Yeah, of course. We always need ILU, because ILU is something that we, even if we don't do those arithmetic operations, just for adding program counter, we need an ILU. So, or other controlling things. ILU is necessary. What else do we have program counter? Yeah, program counter we also need, because we are writing a general purpose computer, and general purpose computer can execute one list of instructions, and program counter gonna go one by one. So we need that as well, and other components, like for example, we need multiplexer, of course, because multiplexer, anytime we want to select between 2 values, we need multiplexer, and probably more. We can see. So this is the first step. Specify which operation this processor is supposed to do. Why we are not considering a complete structure? So we want to simplify data paths. When we simplify, we can highlight the key components of that, and you can use that in other purposes, in other applications, other processor. So I want to give you the idea. That's why we start with a very simple, simplified version of RISC-V. And you also, anytime you want, you can extend that. You can make that more complicated. You can add more stuff to that structure. Okay, so that was the first. The second part, we're gonna review. We had these types before in RISC-V is the same. Here is also the same. The first type of instructions is a R-type instruction. Here we can learn how we can design instruction. This is instruction, has instruction that I'm saying, it means in terms of the, like in a machine code, 0 and 1, not in assembly part. Okay, so R-type, like add, sub, and shift, and they have 3 operand operator. So we have 1 destination and 2 source. Based on the size of the register file, we consider the multiple bit that we need. Like, for example, in this computer, we consider, first of all, size of instructions, 32 bits. And we are assuming the size of register file is 32. That's why we just need 5. So register destination is 5, register source is also 5 bits. Okay, opcode specify the type of instruction, like R-type, and these 2 functions also help that to specify which instruction in R-type. For example, AND. With changing this 2, we can make different instructions. So why we need this opcode? Opcode actually is very important because opcode gonna tell controller which control signal produce. So the control signals are created based on opcode and these functions together. Because this opcode and these functions together specify which instruction is this. So the controller need to make control signals. Control signals are like a brain of the computer, main part of the processor. Okay. As I explained, most of the time we can explain instructions with the structure that we call it register transfer language, RTL. In this register transfer language, we specify source registers, operation, and this arrow showing where the result's supposed to be. For access registers, it's very simple like that. If you want to access memory, we have also the similar, we put mem. We're going to see that in next slide. And instruction format is 32 bits. Based on that, I already explained. It's exactly similar to RISC-V. We didn't change that. And opcode is instruction type, register destination, register sources. Function 3 and function 7 specify the exact operation. This function 3 and opcode together give controller to decide which control signals need to be 0, which control signal need to be 1. What is control signals? Control signals are all control inputs of all components. All of components in computer, they have some inputs, control inputs. These control inputs tell that component what to do. For example, ILU as a component has 1 control input that is called operation. Which operation ILU supposed to do? We tell that with a couple of bits. And for memory also, we have control input. For registers, we have control inputs. For multiplexer, also we have control inputs. Do you remember what is the control input for multiplexer? Selects. Perfect. We have selects, remember? selects are the control inputs. Perfect. So this is R type. The control unit, as I explained, interpret these fields to generate data path control signals. You can see, and this design that we are doing, everything supposed to do, everything supposed to finished between clocks from here to here. Okay. Okay. When I explain the component, I will tell you which components get activated with this signal, with these edges. So the components normally that changing state need to get affected. Okay, let's go ahead. We're going to talk about that more. Let's go for I type. I type is for immediate, and immediate load is also considered immediate, because when you are loading something from memory, you have a base address and one immediate value that's going to get added with that register to make this is the RTL language for access memory. Register transfer language. As you can see, when we put memory here, it means the value inside this address. When we put this bracket, showing inside is an address. It's an address. And we are accessing to the value of that address and put that value in register 5. Okay, so this is the RTL version. So RTL the reason that I'm talking about this RTL, sometimes you just can write whatever computer supposed to do using these RTLs. RTLs is like a high-level language. And then you can change RTL to Verilog easily, similar to that, and run it by microcontroller. Okay, so that's a load. For immediate, also we have add immediate or subtract immediate. When we have one value as a constant that need to get, for example, here add immediate with register 6 and result go to register 5. So this is also RTL, as you can see. You can show, you can use immediate values in that. 10 is like a constant number. So the format for immediate still formats all 32 bits because we want to make the processor regular. Everything needs to be similar to not make problem. The reason is to make everything done similarly and in the same time. So that's why all instructions are 32. Maybe you ask me, is any computer that the size of instructions not similar? Yeah, the computer that you are working right now, if it's Intel or AMD, they're not like that. They're not RISC. They're not RISC instruction set architecture, reduced instruction set architecture. They are CISC, complex. In that complex, they have different instructions, different size, different timing, even for fetch. Fetch, because fetch is they take the instruction out of the memory and decode it. Anyway, that's instruction for I-type. Still, you have opcode. You have some functions. You have registered destination. You have registered one source, one immediate value. This immediate value is 12 bits, so 2 power 12 bits is the maximum number that you can put there. Okay, so as I mentioned, right now we also can learn how to design these instructions. How we can design instructions, you need to know based on the number of instructions, number of registers, and at the maximum number of immediate values, you can change and play whatever instruction you like. In this example, because we want it to be similar to RISC-V, we consider that 32. But in your design, that for the computer that you're supposed to design in this class, maybe you decide 16-bit instruction. Don't need 32 bits, too much maybe. Okay, and so opcode is instruction type, that is I type. Register data, RD, register source, we just have one. And function tree specify which operation type. We have I type, but operation type, we might have different I type, that this function tree, these 3 bits specify that one. Immediate is an immediate constant. Okay, that's I type. It's exactly similar to RISC-V. A J type is also for jump. Oh, for a store is also is another type called S type. Before going that, I should mention that as well. We also have S type, a store type, like when we are saying store a word, x5 and 8x10. We are using the base address. This addressing is called based or based addressing. I think it's based, not based. Addressing, because we have different type of addressing. Base addressing is when you have a base. This is x10 is a base, and you have index that like RTL for this. Let I change the color to show that nicer. Is whatever is in a memory in the address x10 plus 8 gonna get moved to x5. This is the RTL language. As you can see, this order is not always that side. We can go this way too. However, it doesn't matter. You can put this way too, but from this side anyway. So that's the RTL. So this RTL language can be changed to Verilog easily. In Verilog, we have similar things. You can do that. So this type of instructions also have different formats. So the format, the opcode is the same. Let's see if I have the, yeah, I have it here. We have opcode here. Opcode we don't have registered destination because destination is memory. We have function tree is the same. We have register source 1 is the same. We have register source 2 is the same as the others, but this one doesn't have. And these two parts are immediate part together. Immediate, this is 5 to 11, 5 to 11, and this is immediate 0 to 4. So the rest are the same. Like function is exactly function, 3 bits. Register source is 5 bits. Instead of having immediate all together, we have these two parts. Why? Because we want it to be similar to the others. Okay, another things, in your design, you are free to design whatever you like. As far as you can implement the rest, as far as it's regular, as far as it's everything similar, it's okay. You don't need to follow exactly what, for example, RISC-V doing. Like this part is different than MIPS, because MIPS is like a grandfather of RISC-V, but this part is not similar, it's different. Anyway. J-type, as I mentioned, is for jump, like JAL, jump and link. For example, jump and link, not just jump, not just changing program counter, but also increase program counter to go to the next instruction. So as you can see here, the RTL language The RTL has two parts. You're adding program counter to 4 and put it to x1 as a destination. That's called the link part. And also you are jumping to the target. And this type of addressing is actually PC relative addressing. Do you remember? We mentioned this. This is PC relative addressing. When I'm talking about addressing, is addressing of operands. Yeah, that's operand. Yeah. Okay, so that's called PC relative. Why is PC relative? Because it's based on PC. You're doing that. However, in RISC-V, we always shift that to right 1 bit because these addresses were always even. The addresses were always even. Why they are even? Because the size of the instructions are 32 is even. So always least significant is already 0. We don't need to save it. You know that. So we don't need to have one extra bit just to put 0 on that. That's why we shift that to get one extra and consider that for jumping. Okay, we had that before as well. So this is the same as what we explained before about J-type. So what else we have about that? This instruction is jump to a new address and also return, store the return address. I mean, program counter plus 4. And a structure is like that. So we have opcode, 7 bits opcode, register destination, because we have destination. We need to save the program counter plus 4. You can come back and register destination. And the rest are immediate. But immediate, as you can see, are just distributed around to be similar to the other parts. That's the reason. Okay, that's a J type. This is another type of instruction. So as we can see, opcode, register, destination, and immediate. And PC relative, as I explained, here is another addressing PC relative. A new PC is like old PC plus immediate, and is a sign extended because you can jump up and down and shift it left. Shift it left. Oh, OK. When we want to put it, shift it right. But when we want to find the address, shift it left. That's the point. Shift it left. When we want to use it, the number need to multiply by 2. OK, that's the reason. Perfect. Any question about this? Did you get why we multiply that by 2? Any things not clear? Okay, so that's good. So this is a very important part of designing a computer. Instruction, execution, stage, or cycle. Sometimes we call it execution cycle. What cycles we need for executing instructions. That's actually one of the important part of designing a computer. I can say most of computers, maybe all of computers, following similar things. Some of them maybe doesn't have this part, but they, in this computer or the family of RISC, we need these steps. We need fetch. We call that instruction fetch. We decode it, instruction decode. We have execute. We have memory to write. If we access memory, sometimes some instructions doesn't need a step for memory, but still we need to have it in this cycle. And write back is to put the result back to where? What do you think? Write back gonna put the result where? Registers, not memory. We don't write back in memory. We always put in registers. Write back in memory, it might happen here if the instruction is read from memory. But this write back is just for registers. Okay, let's explain one by one. Instruction fetch. Instruction fetch is, okay, so we need to know some information. First of all, there are programs in a memory, but in a specific part of the memory called instruction memory or program memory. So instruction memory or program memory is the part of the memory, general memory, that is specified for the code. The code is there. Somebody need to point it, and that is a program counter. So the program counter specifies which instruction need to get fetch. When we fetch instruction from the memory, this is instruction memory. Have some instructions. When we fetch that, where we put the result, what do you think? Where we put the result? Memory is not in the CPU, it's outside. So when we take that instruction is 0 and 1, based on those structure that we mentioned for I type, R type, whatever. So where we put the result? Inside the CPU, of course. Is any specific place for that? Yes. And that's called instruction register. So we have an instruction register just for that. We have a specific register just for that. What's the size of this register in this computer? 64 or 32? What you said? 32, because size of the instruction is 32. Even though the computer is 64 bits, but the size of instructions is 32, so it's 32. Okay, so in this computer, instruction register is 32 bits. Because whatever instruction we designed were 32 bits. Okay, so that's the first step. Let's clean this up. The next one is a decode, instruction decode. So instruction decode means decoder. So decoder, you need to have decoder to decode opcode based on the opcode. And those fields, extra fields like 3 bits and 7 bits, together specify the instruction. Instruction decode actually interpret instruction fields, I mean the opcode, and identify registers and operation types, whatever we need. Also, we access to register file as well. So when we got instruction register, this is going to a decoder, and this decoder specify, actually this decoder is part of the control that specifies some signals that, for example, if you are register type, you need to read data from register file. Or if you have immediate, you need to do immediate. If you have some selection, you need to specify the selection. That's called decoding. So instruction decode is actually control. Decoder is the control of the computer. Instruction decode is something that controller supposed to do. Decode what? Decode opcode, and those extra function that we had. Okay, that's a decode. After decode, we need to execute. What execute means? It means we need to, after decoding, we make some signals for ILU. Execution is for ILU, arithmetic logic unit. So arithmetic logic unit also has some control, like which operation supposed to do. ILU doing multiple operations, not just one. Do multiplication, for example, do addition, subtraction, whatever. We need to specify that. That's the operation part. So we specify that as well. That's called execution or EX. So perform arithmetic or logic operation using ILU and compute branch or memory address. So it's not just for register type instructions. Sometimes for access memory, also ILU involved. As I mentioned, because we need to compute the address. So we need to add, for example, or subtract. So computing branch or memory address is also part of ILU. So that's execution. When we are done with execution, we go for memory access. If or instruction is a memory instruction, we need to read from memory or write to memory. Okay, and the result need to write back to the register file again. So in this step, we just have, and all of this step need to be done between these two. Anybody can tell me which of these operations gonna be done here, which one need to be done between, and which one in this edge. First edge. Tell me which of these, just one of them, need to be done, actually even not one, half of the one, need to be done in this. Okay, so we need to see what is a state here. A state in this process is a sequential design, isn't it? So the state of this is specified with program counter. That's one of the registers that need to change every time. So that's the state. It's changing every time. So program counter, this is with program counter. So this is connecting with program counter. And what about last one? I told the first one, but last one probably is somewhere here, the last, of course. And that's true. When we want to write back in the destination register, that's happening. That's clock synchronizing register file. So one going to program counter, one going to register file. Maybe you ask me, what about memory? Memory doesn't need clock. Memory, when you put the address, the output gonna ready right away. Doesn't need clock. In this design, we just need, when we are finishing the design, when we want to connect clock, we just connect clock to program counter and register file. Register files, all registers are together. So this is for register write, when we want to write to register. And the others all happening between, like instruction fetch, the part of instruction fetch, instruction decode, execute, memory, they are all happening in here. Instruction fetch, part of instruction fetch, instruction decode, execute, memory, happening in this between. Okay, that was, okay, so we don't have time for that. Okay, so we're going to talk about this next week. however, we already explained this, the main component. Let's finish that, and next slide. We already talked about this last class. We have some components: program counter, instruction memory, register file, ILU, data memory. And for this specific type of computer is a part of the design. We need to see which of these components need to get used. Because this computer is almost a full computer, we need all of them. And for data path, as I explained, is a start from here. This program counter specify one address, and when the address get ready, this is memory, doesn't need clock. Right away, very fast, read the instruction, put instruction in the register, instruction register, and instruction register specify these register numbers. And when these register numbers get ready, the output get ready without clock. In these two, and ILU do operation. We have another part, control here, to give signals. We're going to see that later. And then if there is something about memory, we do that. Other than that, we don't go to this part. We're just switching from here. From here, come back to this data. And the next clock coming, the data gonna write back. So this is called data flow in the processor. Okay, we're gonna talk about them more next time, and we're gonna see how we can implement that using Verilog. Okay, have a great weekend. If you have any question about your exam, let me know.